Hey, this is Dr. Della Corte with the last lecture in our series on quantum computing, where we are going to look into the impact of quantum computing. We have learned a lot so far. We have learned how measurements impact states of spins and qubits. We also talked about linear algebra and how we can use the fundamental principles here to do calculations that were necessary to derive the algorithms we discussed last time. We talked about actualization of qubits through spins and polarization of photons. We saw what entanglement meant and how two states can become so interwoven that even after separating individual qubits by a certain distance, changing one of them will still impact the other one. And we saw that that is actually um, a global property that links entangled entities together, and it's not so much the result of a hidden variable as we have seen through the Bell test. We talked about different gates, first the classical gates, and then finally the quantum gates. And we used those to illuminate the terms, catchy terms, super dense coding and quantum teleportation, to simply mean sending two bits at the cost of one qubit, or to send the state of one qubit at the cost of two bits. And those are nice things, but they might be a little bit too hyped, just giving the naming and the media attention they get at times. Last time we then looked into the different quantum algorithms. We saw, for example, the Deutsch algorithm that was able to use just a single call to a quantum calculation black box that would allow us to figure out if a function is either balanced or constant. We saw how that can be generalized to a function with n inputs, and still the quantum algorithm would only take one call to the function. And we said that this number of callings gives us the so-called query complexity, which is an easier way of comparing the efficiency of algorithms, although maybe not the most fair one in terms of speed. Okay, and then finally we talked about Simon's algorithm and how it can be used to find a secret string. And we saw that the basic idea there required the generation of a random string through a quantum algorithm, and then this solution of a effectively system of linear equations through a classical computing algorithm. Okay, so the basis of all of these algorithms was always that we could use the superpower of quantum calculations to put inputs into superpositions, and then we could use the structure of the problem after running it through some Hadamard matrices or some other orthogonal matrix to find a structure that then would allow us to amplify the probability amplitude of certain outcomes. And that helped us then to deduce the results of the algorithm with way fewer calls than in the classical equivalent. Great. So let's talk about something else today. Today we're going to talk very high level about two algorithms. One of them is Shor's algorithm, and the other one is going to be Grover's algorithm. We're going to talk about Shor because there's oftentimes this big fear mongering out there that once we have quantum computers, internet won't be safe anymore. And in order to understand what this Shor's algorithm does, we first have to understand the basic encryption scheme on which many communications in the internet are based, which is the so-called RSA encryption. And I'm going to use the example of a user communicating with a bank to walk you through how that currently is being done. And then we're going to see why Shor's algorithm can be a potential threat to this safety guard. So if you as a user want to send data to the bank, but there's potentially this evil Eve around that wants to get your data, you want to try to prevent Eve from ever seeing what you communicate to the bank. And the way you can do that is by making sure that the user and the bank both have a key that can be used to encode and decode a message. But the question is, how do you get the key from the user to the bank, right? So one thing we can do and this is this RSA encryption, is we let the user create a key. Okay, the user creates it on his device and he knows it, but the bank doesn't know it yet. What the bank does, it finds two very large primes, P and Q, and he uses those to find a small number E that has no common factors with P minus 1 and Q minus 1. So you randomly draw two numbers and then you find another number E that has no common factors with P minus 1, Q minus 1. That's not hard to do. You can do it very fast. And then the bank calculates a number N, which is the product of the two large primes P and Q. So this is really where all the safety hinges on, that this product N is a large number over 300 digits, which is very, very hard. We saw it last time. If I give you that number, it's very hard to take that number and find its prime factors. Yeah, that's where all the security is based on this concept. And I'll show you why. So when this bank has calculated this number N, it sends the numbers N and E back to the user. The user now takes his key E, exponentiates it by E, and then calculates the remainder by modulo division by N. And then this number that the user creates is being sent back to the bank. Now, if the entire time while the user sends things over and the bank sends things over, Eve has been listening in on the communication, Eve would then know this product here, or this remainder, k raised to e modulo n, and it would be aware of the number n and the number e. Okay, so what would Eve like to know? Eve would like to know the key k. Is it possible to get k for her? So in order to calculate k, we would need to know the factors p and q of n. And that is something that we think is very hard to get because finding the primes of a 300-digit number is very difficult. So what the bank does instead, it calculates k because it knows all of the missing factors. And since now the user that created k in the bank that has calculated k have the same key, now the user can use the key to encrypt the remainder of his communication and send it to the bank. And even if Eve drops in and steals whatever is being communicated in the future, without the key k, there's no value in the data. So the entire safety is ensured by the fact that factoring n into p and q is a hard task. Now, the basic idea of Shor's algorithm is that it might make it very feasible to do the factoring of even such large numbers on a quantum computer. Okay, so here's a little picture of our friend Shor. What he realized is that Simon's algorithm had some interesting properties in how it emphasized and canceled amplitudes because of how the Hadamard matrix worked. What Shor realized is something very similar is true for the behavior of the so-called quantum Fourier matrix. We won't go into the details of that, but just as a basic idea here, understanding Simon's algorithm well enough and seeing a symmetry to a different problem allowed Shor to come up with the following. He said that if we have this number n, that is the product of two primes p and q, you just have to go ahead and guess a number a that is somewhere between 1 and n, and then check if a has any common factors with n. If it does have, then you're almost done. You just have to calculate the remainder of a modulo n, a to the square modulo n, and so on. And then as you calculate the remainder, eventually that number will repeat. And as that modulo remainder repeats, you have this relationship that a to the power r, so that is the r power of a modulo n is equal to a to the power 1 modulo n. And once you find that equality here, you know this number r, which we call a period, after which you get a repetition in these remainders. And once you have this number r, you can use that in the classical algorithm to find the factors of n. Okay, so now this is a little bit hand waving here because I'm just telling you that, but we don't want to go into the depth today. So I'm just telling you, mainly because of the math that's involved. It's going to be way more than our lecture 2 on the algebra that's going to be required to understand this. Um, so effectively, what we want to be able to do is similar to the assignments algorithm that found a secret string S by randomly guessing some numbers or some strings that were orthogonal to S, so that the dot product of 0 with S. You can also use the generalization of Simon's algorithm to find this number R. You can see a little bit like the symmetry of Simon's algorithm. There's going to be a factor on the left side. It's kind of like the secret string that causes this equation to be true. So there's a way of guessing this number R. And Shor showed that with a quantum algorithm, you can do that potentially very quickly, and then any large number can be factored. And so if we want to have safe internet at the time of quantum computers being available for anyone, we need to make sure that encryption or safe, secure communication is resilient to not only the classical attacks we know today, but also potentially quantum attacks. And we already learned about the BB84 and the Eckert's protocol that could actually use quantum computing, on the other hand, to safeguard communications. And honestly, while many people are concerned about the implication of Shor's algorithm, if you think about it in depth and look into the literature, there's already a whole field of quantum cryptography that goes around, and we have alternatives. Setting a new standard and getting everyone to adopt it is going to be painful, but it will be completely doable. So while Shor's algorithm is solving a big and important problem, I don't think we have to have doomsday fear of the quantum computer coming out and performing these actions. Once it's being developed, people will know about it, it will get published, and then security measures will just adjust to a new way of encrypting things. By the way, just to give you a feeling for what has been done in the year 2022, this number here with 3, 6, 9, 12, 14 significant digits, 15, 15 decimal points, no decimal points, what do you call it here? What's the number even? I don't know. This is a really large number, but it has 16 digits, was people were able to factor it. So they wrote a paper about factoring that large number. If we want, oh no, actually, I think this one got factored with a quantum computer with a few qubits. So this is why it's cool. Otherwise, you wouldn't get a paper with that. But yeah, this number here can be factored now, but it's still far off from 300 digits. So we're not too concerned at this point. Great. However, if you look into the quantum key distribution market, people are trying to invest money. And so while last year you could maybe get $500 million, by 2030 you might get $2.5 billion market share to capture. So if you want to learn about it, you have 5 more years. Okay, great. Let's talk about another algorithm that has promise. This is Grover's algorithm that is can be used to speed up the search of data. So here's the problem, as by the way, Grover here on the right. Let's assume we have a set of cards, and one of these cards is the King of Hearts. And the question is, how many times do I need to flip a card before I can find the King of Hearts underneath it? So let's say I flip the first card and some other card, throw it away. Flip another card and something else, throw it away. Flip another one, oh, I got again lucky, throw it away. Now, do I need to flip this card? Not if I believe the rules of the game. If I know there's a King of Hearts, I know that's under there and I'm done. So if I had 4 cards, I needed to do 4 cards, I needed to do 3 calls and -1. But of course, someone might have rigged it, so I might want to flip it and just to be safe. Okay, so it would take me classically, in the worst case, n-1 queries to find out if a card has a certain face value. You can encode this problem also in bits. If you, for example, ask the question, how often do I have to call a function with 2 inputs before I find the 2 inputs that give me a result of 1? So if I have these 2 bits, then there are 4 options that I can put in as inputs. The question is, how often do I have to call this function before I at least get once the value 1 returned? And same problem. I can get unlucky and I have to call 3 times and get zeros, and then now the last call will give me the 1. So we're having here a query complexity, right? How often do I need to call the function f? So let's just construct a gate that helps us to solve it. So we're going to take 2 qubits here that come in, a 0 and a 1. We put them in here in there as the tensor product. We run them through the gate f. And then we also have a control bit y here that's being passed in. And then we get the superposition or the tensor product up here, and then the C naught of whatever the function does with the inputs with the y state. Okay, cool. What will this function f look like? Well, you could have guessed it. We're going to use some Hadamard matrices, which we're going to do. And then once you run things through the Hadamard matrices, the 1 state is going to be put into the standard superposition. The 0, 0 state is going to run through this little bit more complicated Hadamard matrix kind of tensor product with itself. And once that runs through, we're going to get out of the F gate the combination of both states that will look like that. So after this Hadamard gate, we're going to have a superposition of the 4 states. Here we have a superposition of these 2 states. Combining them gives us 2, I guess 3 qubits in this case that live in these states. Okay, great. And now what you might notice is there is, after that F gate, there is only one state of the top 2 qubits that has a minus sign. All the other ones have a plus. Only one of them has a minus. And the idea is that running through this gate here, or the circuit, allows us to flip only the bit of the function that actually produces a value 1 and not of the others. Okay, so let's look at this a little bit closer. We just want to measure the spin flip here. So if we write out this top superposition, it looks like this. And now if we measure this, there's a certain probability that we get the 1, 0 state, which is the state that we would want. But it seems to have the same probability of a quarter as all the other ones. So we would want to increase the probability of measuring the state 1, 0. And the way we do that is by a nice mathematical trick called the amplitude amplification by flipping around the mean. And what that does is it says, hey, if I am able to change my amplitudes of the 3 states that I don't care about to lower values closer to 0, and the one that I care about closer to 1, I will eventually be able to only measure state 1. And how do you do something like that? Well, you simply really calculate just the mean of these 4 values, and then you flip the one. So what's the mean here? It's 3/4 minus 1/2, whatever the value is, half. Was it half of a third? Well, I don't know, but you can calculate the mean, and then you flip it around it, and you will see that this amplitude here will be further away now from the 0 than the other ones, and so you amplify it. The matrix that computes this flipped amplitude is shown here, at least for the 2-dimensional case here with 2 spins. And so after you apply it, it is going to increase the probability. Actually, in this case, it works out that it gets you 100% probability of just getting this one flipped state. And with that, you're done. Because after you measure it, you know the state 1, 0. And then since you know 100% the state 1, 0, you know that was the card to flip, or the function that was called. So that's pretty cool. But what is if you have larger number of cards? So right now this is for 4 cards only. What if you have a very large number of cards? If you do have like 36 or 32 cards, you will want to run through the circuit multiple times. And every time you run through the circle, so you have 32 possible cards that can be flipped up. And initially, they all have the same probability. But as you run through it multiple times, you keep on increasing the probability um, for the state that you are most interested in. So it turns out that you need to use the square root of the number of cards, m, as the number of calls. Okay, so square root of m is good compared to m minus 1 calls, where you had to look at everything. So it's a quadratic speedup. That's pretty cool. Of course, what happens if you have a database that you're searching for and you try to find one specific thing? And in a classical sense, you would never start at the beginning and look through everything until you may or may not find the thing you're looking for. There's typically some structure to the database you can use to jump around and sample more quickly or more efficiently. And then a classical search algorithm will perform very well. Otherwise, Google wouldn't get us as far as it does. Um, so this is, again, a very simplistic view of how search can be optimized, but it is very powerful in its principle. One of the key questions, of course, is what if I'm calling this magical function f is a very expensive operation? Even if I only have to do it square root of m times, if each call is more than quadratically expensive compared to just calling doing the classical approach, then it might not be worth it. And so in most cases, the quantum calculation will actually be quite expensive. So it will take a while before we have the software and hardware to make that feasible to really use. And then is it really a problem that databases might have a structure? Well, yes and no, because Grover could take advantage of a structure as well. If there's, for example, a subset that only has to be searched through, then Grover could just be applied to that subset. And what about the quadratic speedup? Is that the best we can do? It turns out no. There are different ways to go from here. And so Grover is, again, one of the fundamental algorithms that sort of opened up a field of possibilities. And currently there are quite a few developments on top of it that you can read up on. And if you want to get into optimizing search with quantum computers, there's going to be a lot of work being done over the next few years in this area. Okay, so the main takeaway we have from this is that Shor and Grover are very important algorithms because they actually solve real problems, right? We factor large numbers, which we can't do before, or we find things faster, which is always important. And the basic idea behind both of them was that we increase the amplitude of the output that we're most interested in. And that helps us to find the desired outcome more quickly. Great. Now, this is the end of the algorithms that we are going to cover, but there are lots more. So if you follow the link here that's hidden, the quantumalgorithmzoo.org, you will find a bunch of algorithms, the ones that we've covered so far on there, and then a lot of others. So that's, if you're interested in algorithms and whatnot, that's a great place to look out for other interesting topics. So an area that I'm personally interested in and I'm trying to learn more about as we go along is quantum chemistry and quantum simulations. So the field that my research is dealing with is how can we use the information of single atoms and assemblies of atoms as they interact with each other to predict, for example, how small substrates bind to a protein, or what energy differences are there on a reaction path that make it easier for a certain reaction to take place within a protein, so-called enzyme, compared to outside of it. And if we understand that well, how can we use these insights to either construct new small molecules that could, for example, be used as drugs, or new proteins, new enzymes that could be used, for example, in bioreactors? So that's kind of research areas that I'm interested in. And so how could a quantum computer help? Well, I think that the fundamental idea of writing out Schrödinger's equations is always a good starting point. Of course, when you have a large system, it's completely intractable to take even just care of all of the electrons around a single carbon atom. It gets tricky. So you want to be able to find ways to solve that. Classically, people use density functional theory and other approaches to calculate that, and then might even generate training sets that are being used in deep learning and machine learning databases to train algorithms that are faster to evaluate and somewhat empirical, but they do a good job. So classically, there are lots of things, and there's many, many research groups working on this. However, if it would be possible for us to truly observe what happens in these reactions, we might be able to get very high quality data sets that could get us even further. And so if we are able to not only simulate in a classic computer the chemical reactions, but maybe use qubits to emulate the chemical reactions, we might be able to learn things from it that allow us to create better data sets, which in the next iteration could then be the foundation for approximations like a deep learning network or something like that. So that's all very interesting. And yeah, so hopefully we learn something together about this as we continue our discussion in the course and throughout this spring. Then computer hardware. So if you want to actually make qubits, you need to be able to store them somewhere. And as we have seen, every measurement is changing qubits. If they're entangled, they can change a whole cascade of qubits. So you have to be able to keep them in their state where they're somewhat stable. And so oftentimes the word coherence is being used to describe the lifetime, so to say, of a qubit. Different implementations of qubits that we have seen in this class are, for example, photons, which are great for communication because they travel so fast. But because they travel so fast and they have no mass, they're really hard to store anywhere. So that's pro and cons. Electrons and nuclei, they appear to work pretty well for 1 or 2 qubit states, but if you want to go to like 200, 300 qubits, they just don't scale very well, and it's tricky to do. An area that we're pretty interested in is called trapped ions. And during lecture, we're actually going to have a guest speaker that works at the National Institute of Standards and Technology, NIST, and he's going to talk to us about how they're trapping ions right now and what are the pros and cons of that process. And then, of course, you have the commercial entities like IBM or D-Wave to a degree that are using different ways of trapping, for example, electrons within superconductors. So there are different ways of how hardware is currently being developed, and I anticipate there are going to be many other smart ideas in the future of how to make this work. Still looking forward for the day when we can verify room temperature superconductors, then a lot of things will become way more feasible. But that's a different topic. Okay, then another word we want to talk about is called quantum supremacy. Again, sounds like a wonderful title for a movie. So let's see what that means. Quantum supremacy defines a point in time when we are able to run an algorithm on a quantum computer that cannot be run on a classical computer. So if there's something that we can solve on a quantum computer that just cannot even simulate on any classical computer, then we have quantum supremacy, or the moment in which quantum computers are better than classical computers. Now, since classical computers improve all the time, and especially with the magic of deep learning going on, and people like Demis from DeepMind walking around and saying that we will probably never even need a quantum computer because machine learning can approximate everything away that you need these machines for. It's a moving target when quantum supremacy can be reached. But the basic idea is in the moment where you can run things on more qubits, you get an exponential growth in the basic vectors that can be represented. And so with a certain number of qubits in space, you can quickly reach a number so gigantic that there are not even enough atoms in the universe to support the calculation on any classical hardware. So even if you have 72 qubits, the number of basis elements is already pretty large, but that is which yeah, it's a very, very large number. And so some people say that might be, I think that was in 2019, probably by now it's more like 100 qubits or so. That's considered to be the threshold. Okay, there are obviously always news articles and people doing marketing. For example, D-Wave in March of this year, of 2025, said that they reached the quantum supremacy because they built these very specific quantum computers, but they're very limited in what they can be used for. And so quite a bit of researchers got upset about that claim. And so some of the advantages that this company made got lost in the media outrage that resulted in their statements. Okay. Of course, in a moment where we go to like 300 qubits, then we have also philosophical questions like when we have 300 qubits and they calculate something for us, and you have these superposition of states, they somehow must exist somewhere. And how does that work? And David Deutsch is one of the guys that has thought about this a lot and published some interesting books that I still have to read, to be honest, but effectively exploring this idea of a multiverse and different universes all chiming in into how things are being calculated in our reality, which is just a branch. And if you've seen any of the Marvel movies, they make no sense anymore. So, well, we're trying to wrap our minds still around the implications. And as we said earlier, the Copenhagen interpretation of quantum mechanics is a bit weird, right? Complete randomness, arbitrariness. If we stick to it, I think we can solve interesting problems. We can build on it. But as these quantum computers evolve, I assume that our philosophy around them will also mature, and maybe at one point we'll be able to have the next Richard Feynman come along and explain the world to us. Great. One thing we can take away, though, is a new appreciation for what computation truly is. So the classical computers are Turing machines. They have been built effectively to mimic what humans do and to automate many of those tasks. So they are a way of approximating our behavior and the way we are thinking and acting. A quantum computer, on the other hand, seems to be more aligned with how the universe overall is computing things and doing things. So we saw that a quantum computer in theory can simulate anything that the classical computer can do simply by don't use superpositions, just use zeros and ones. But that's not true vice versa. So a classical computer is not able to handle the superposition of an arbitrary number of qubits. So that is why we call the quantum computer the more general computer, or quantum computing the more general form of computing. Or if you want to think about it a bit more abstractly, you might say that classical computing is the computing that's centered on humans, while the quantum computing is actually how the universe operates. So that's a bit similar to how Copernicus and Darwin challenged the worldview of where we are in the universe and where we are in the creation plan of a God, from being human-centered, Earth-centered universe, human-centered evolution, to a more diverse, broader, mind-boggling universe in which many, many things are happening, given with interesting probability distributions, but given the infinite space of the universe, everything seems to be happening somewhere at least once. So it's quite interesting. And I'm not a philosopher, so I don't want to go too deeply into it. But the idea that quantum computing might cause a similar shift in thinking as Copernicus and Darwin is intriguing. And so you might want to write a couple of sentences in your study journal on how you position yourself on that debate. So finally, let's end with a quote by Chris Barnard. And before I read it out, I say thanks for being here. And if you're part of the course, I'm glad to get to know you better in class. And if you just listened in, I hope you took something away from it. If there are any suggestions for what to do next or what to do better, this was more or less me going through the slides the very first time, a bit of PowerPoint karaoke. But I hope that you took something away from it. And maybe at some point in the future, I'll have the time and interest to re-record things. So if you want to leave me some notes, I'm happy to take that feedback into account. So now, Chris Barnard, before I say goodbye. We are entering a new era. with a new way of thinking about what computation really is. What we're going to discover is impossible to say, but now is the time for exploration and innovation. The greatest years of quantum computation are ahead of us.